Good morning. Thank you for joining part 5 of our 6-part Open-NFP summer webinar series. Today, Mark Matties is going to present Protecting the Privacy of the Network using P4 to prototype and extend network protocols. Securing sensitive data must go beyond the encryption of the application and its associated data. Mark's team is developing a protocol to encrypt layer 3 headers so that the network information is also remains secure and private. Using P4, they are able to rapidly stand up and prototype the proposed solution in real code running across real devices. In this webinar, Mark will introduce their approach and how they used an extended P4 functionality to stand up a prototype. A copy of this presentation, archived replay, as well as any project code will be made available shortly after the webinar. These, as well as our previous webinars, can all be found on the classroom page on the open-nfp.org website. Mark Matties is the Chief Scientist in the Communication and Networking Systems Group at the Johns Hopkins University Applied Physics Lab, where he develops and evaluates SDN solutions to improve network security and performance. He holds a BS in chemistry and a Ph.D. in Polymer Science and has worked for over 20 years in computing, networking, and security. And then let me tell you a little bit about Open-NFP before I turn it over to Mark. Open-NFP's objective is to support and grow reusable applied research in data plane network functions processing. We do this by focusing on reducing the barriers to performing research in this space to researchers and developers creating, implementing, and verifying their ideas on production networking hardware. Open-NFP supports research in a wide range of technologies, including software-defined networking, OpenFlow, OpenFeed switch, and P4. We support researchers with a variety of tools, including deeply discounted hardware, IDE software, and community cloud access to development systems, and direct support from our engineers in a research community. We also provide support to learning advanced networking concepts on our hardware through tutorials and seminars, such as the one we are performing today. We encourage proposals to research funding agencies. We invite you to join the 20+ universities and companies working directly with Open-NFP through projects. Thank you, and I'll turn it over to Mark.
Okay, so just want to double check that you can hear me okay.
Yes, we can.
Okay, great. So thanks for the introduction, and I'm going to, I have a set of slides to go through, but I always prefer a conversation to monologue. So I think that there's either a questions box or chat box. If you have short questions that you'd like to ask along the way, please do so. Otherwise, I think that they'll be collecting questions, the longer questions to answer at the end. And I can always be reached by email at mark.matties@jhuapl.edu. So let's get started. There we go. So the motivation for this work is, and this is opinion, my opinion, is that privacy protection currently is incomplete. We tend to focus only on the end hosts to protect sensitive information by encrypting it and, either at rest or in transit. And this is done in a, let me say, a hit or miss kind of way, where some data may be encrypted, some may not. And we all know SSL and TLS. And so if you have that enabled on your web server, then you can have encrypted application data. If you happen to be running IPsec, much less common, of course, than TLS, then the layer 3 payload is encrypted, but nothing about the network itself is protected. The privacy is not protected. So I contend that there is sensitive information in the headers. That sensitive information is, for example, the hosts. So, you know, by looking at headers, you can find valid hosts on a network, particular for IPv4, and if you happen to be using type of service, quality of service, and you set those bits, then you're further exposing information about the packets, even if the payload's encrypted. So this layer 3 version I'm talking about now is actually half of the work I've been doing. I've also been doing work at layer 2, but that's much different in terms of being mostly in hardware, where this can be done a lot in software. So if you collect the header and timing of packets, you can of course also do traffic analysis, right? And then if you include in that you're setting type of service bits, then you are leaking information about the network that is useful to an adversary, because as the diagram at the bottom shows, something that we talk about in terms of is a so-called cyber kill chain. But you know, if you look at that and you have any kind of security background, you know, that's just kind of the progression of an attack. And the first step is reconnaissance. So if we can reduce the amount of information that we're exposing, including about the network, then I contend that we're going to be more secure. And then if we do this and we go down this path, there's actually a secondary benefit that comes out of this that I'll talk about. So proposed solution is to encrypt all bytes in transit, including the headers. This can be done independently at layer 2 and 3. I mentioned layer 2. That's kind of a different problem, and they're complementary, but they're not interdependent. We're both working on both, but I'll just talk about the layer 3 today because that's what we can do with P4. The solution we call fully encrypted network communication, FENC or FENC for IP routing. So throughout this talk, I'll be abbreviating that FENC-IPR. So that the goal here is to have the network devices support transmitting and receiving IP datagrams with encrypted headers. So this requires rethinking the protocols, as we'll see shortly. The subsidiary benefit is that now we can define and enforce only authorized forwarding paths, because if the headers are encrypted and a router does not have the key to decrypt that header, then it cannot, of course, route on that packet. You know, of course, nothing new, but as long as it does not impact performance, if we can, we should go ahead and encrypt payload bytes as well, because, as I said, payload encryption may be somewhat common depending on your use case, but it's by no means ubiquitous, so we might as well do that too. And this first try was using IPv4 routing, but really any packet forwarding mechanism, any layer 3 mechanism will work here, and I'll point that out a little bit in the coming slides as well. So here's just a cartoon to kind of set the stage. We've got 2 end hosts connected to networks, series of routers, and oh, by the way, this does not require SDN necessarily. Of course, for us, it's just a lot easier to prototype and control it in an SDN type, and then especially with P4. I actually started doing this project trying to modify just Linux kernel, right? I did not start this doing this with P4, but just trying to modify the network stack of the Linux kernel, and that did not go too well. So I actually went to the developer day and workshop, I think it was back in May, out at Stanford, that Metronome was a part of, and there are lots of Open-NFP type folks there, to learn about P4, because after reading more about it, kind of heard about it at previous conferences, but then digging into it, I thought I could use it, and it turned out to be very, very useful and very quick to prototype this stuff. So here we've got 2 hosts and a series of routers, and basically the set of green arrows that's the path that is the valid forwarding path along those routers between those networks for those 2 hosts. And so we want to lock down that path by encrypting the headers of IPv4 headers of the packets that go across that path. In order to do any kind of encryption, we of course need a key manager. And so what came out of this was that, well, if we're going to have a key manager, if we're going to have keys to do encryption, of course, we've got a couple of choices. One choice is that we could just have, for example, one global key across all the routers, and every packet that came in, no matter what flow it was associated with or what forwarding path, that key would be able to decrypt every packet that came into the router. A second choice would be that we could have a, in this case, not per flow set of keys, because that would kind of be too many. But what we could have is a per forwarding path set of keys. And I'm intentionally using the term forwarding path as opposed to route because for me, I more associate the term route with an IPv4 route. And so in this case, if we're doing IPv4, that's correct, but this could be generally applied to any forwarding protocol, packet forwarding protocol. So along a forwarding path, to get from A to B, if we associate a key with that, then the other routers that are not in that path do not have that key and cannot, as I said before, cannot decrypt that information. So it cannot, in this case, a route on those packets, and they'll just get dropped. So if we want to do this, we need a key associated with a forwarding path. Then kind of backing that up, we need to define forwarding path IDs because we need a table, especially for decryption, when a packet comes in, say from this, when it's sent from this router to the next router, the next hop, the packet is from IPv4 header through the rest of the packet, it's all encrypted, and so now our choices are try to decrypt that with every possible key you have for every possible forwarding path, which with some routers can be many thousands. So that's not practical, of course. Or you can have some kind of clue that to tell you what kind of which key to use. And that clue being the forwarding path ID, or over here in this little table at the end here, FPID. So with each forwarding path ID, we're going to associate a forwarding path key, FPK. And the key manager is going to take information about the network, meaning learning what the valid forwarding paths are, and then it will distribute keys for those forwarding paths based on the forwarding path ID. That part is not done yet. That distribution part is not done yet. In this work, it's all statically configured keys to try and get the basic functionality out. So the problem is, if we have a forwarding, we have to send a forwarding path ID with that packet. And if that's unencrypted as well, then that's still, it's less than maybe the source and destination IP addresses, but it's still a clue about something about the nature of that packet that could be that could have traffic analysis performed on it, looking at the how often and the timing and so on of packets sent from A to B, which we still don't want, right? So we need to encrypt that too. So what comes out of this? Well, here are the components. Kind of the data structure type or associated components are that globally, meaning at least within your domain, unique forwarding path identifier, FPID. So we're going to have that to have to encrypt that forwarding path ID. I'm actually going to put on another header, and that header is going to be encrypted by what we call a logical interface key, which I'll get into in a minute. So that encrypts this new FENC-IPR header that we're going to tack on. Basically, we're going to wrap the IP packet in another header that will also get encrypted. So we've got logical interface keys, for example, between this router interface and that router interface. Those two have do a key exchange, and then the FENC-IPR header gets encrypted by that. So all of that traffic between those two interfaces, the FENC-IPR headers get encrypted. And then the forwarding path, this forwarding path ID for this forwarding path tells which forwarding path key, FPK, then to use to encrypt the layer 3 header. So only routers with that valid forwarding path, FPID, FPK pair can decrypt packets and actually do forwarding, do routing here. So of course there's a big problem of that forwarding path discovery, reporting back to the key manager to do that in a verifiable way, and also then for the key manager to distribute keys. That's a hard problem. That's the next step. We wanted to prove out the functionality of just being able to create these headers and forward based on these headers, which is what I'm talking about today. And then the next step that we're looking toward is to actually have a working key management system. Okay. So here's what we've come up with. Is this added, what we call FENC-IPR header. And its primary purpose is to carry the FPID, but we added a couple other pieces to it because if we're going to encrypt, we're going to have a, operate within the bounds of block sizes for whatever algorithm we're using. In this particular case, because it was simple and well known, we choose AES-128, so that's got a 16-byte block size. So your data needs to be to encrypt needs to be in blocks of integer multiples of 16 bytes. We've got the FENC-IPR header being 32 bytes. We put some other stuff into it. And the part that's encrypted, I'll get down to that in a minute, but the part that's encrypted is actually 16 bytes. So down here, so the primary purpose is to carry the forwarding path ID. What we've done is these two things, the short sig or short signatures or shortened HMAC digital signature, to do a quick authentication check. Because what we also don't want is to try to fix one security problem and introduce another one that's possibly bigger, such as a DDoS attack. So now if I just flood my router that's enabled with this with junk, right, I'm basically fuzzing the router, and try to crash it because it can't handle it, right? So what we're going to do is this short sig is the shortened signature. It's 8 bytes. So we just take 8 bytes out of the HMAC, which is SHA-256. We take the last 8 bytes and stick it in here, and then that is the signature for what's in the blue, what's in the dashed blue. So for the rest of that FENC-IPR header, that's the signature. And we'll see where that comes in shortly. This next short sig is for the next header, which is the encrypted IP header over here. Since I'll just briefly describe this because it's not an encryption webinar, it's a network engineering webinar. So this IV is an initialization vector that we need for the encryption algorithm, and then that plus a symmetric logical interface key. We would have actually public-private key pairs, and then use those. It would there would be a mutual authentication, and then there would be an exchange of a symmetric key, which of course much faster algorithms to encrypt with symmetric key algorithms versus asymmetric key. So we use a symmetric key encryption to encrypt this information. We have the FPID, we have the next type, we have and the next size, and then we have a counter that can serve as a similar kind of initialization vector to encrypt the next header, right? And the next header here is an IP header. I need to, there we go. In the IP header, we'll see a detail in a little bit, but it's the regular IP header. But we need to pad it out. The regular IP header, of course, 20 bytes. We need to pad it out to a multiple of 16 bytes in our case because of AES-128. So we put another counter, or it can be a random value or something, but a required option, right, which is an oxymoron, but It's required because we have to pad out to 16 bytes. So it could be zeros, it could be random. If we then want to encrypt the layer 3 payload down here, then that could be another either counter or initialization vector or something like that, that we can use an 8-byte size, right, to use that to encrypt the layer 3 payload, right. So then back up here in the layer 2 part of the header, that's still plain text for now, and in this work I just use this ether type value of 88B5. There's a set of or a range of ether types that are available, quote, for experimental purposes, so I just picked one, right? So in this example, 88B5 would be for where the layer 3 is IPv4, and then say B6 can be IPv6, and B7 can be MPLS, and whatever you want, right? So that's how we're going to say identify which type of layer 3 we're encrypting. So the deal on this logical interface key, which of course the values that key is going to be different than the forwarding path key, and that's to encrypt that FENC-IPR header so that we don't have the forwarding path ID going over plain text in the packet transmission. And so there's a key exchange in the first phase of operation. There would be a key exchange between either a host and router, and router, and then you get that LIC encrypted link, right, the logical interface key, being able to encrypt the FENC-IPR header. And then in like another phase, there's the forwarding path discovery and key distribution, so that the layer 3, the original layer 3 header gets encrypted according to the forwarding path that's used, right? And then of course, if the forwarding path changes, which can happen, right, if an interface goes down or something else happens, and especially in SDN where we have much more flexibility in how we define forwarding paths, and we want to move a flow from one forwarding path to another, or we want to just change forwarding path. If the forwarding path changes, the key manager in this case has to adjust to that and redistribute keys, and we have to invalidate previous keys after it distributes a new set of keys, etc. So, and then finally we get this total per path encryption of the information, right? So if I go back to this picture, so basically this and everything in the red, this information, it's outlined in red, all that and all this is encrypted. The only thing that's not are the 2 short signatures and the IV, which, right, for normal encryption, the way we practice today, we don't usually encrypt that stuff anyway. So that's the basic idea. So here, for prototyping, I mentioned already, the concept does not specifically necessarily require SDN, but it's just a lot easier that way because, you know, certain incumbents are not giving us their source code. So this is, of course, a very easy way to prototype. And P4 especially, I'll show some code in a minute. New and modified headers, right? New is FENC-IPR, modified is we have to have a required option to pad out the IPv4 header in this case. So that, of course, means new protocols. And so we can use P4 to prototype. And so the benefits that I found for this particular application beyond the usual that we either know about or, you know, if you don't know about, then, you know, you can certainly read about. The benefits beyond this was that P4, I don't know if this was by design or not, either way, you know, thank you all the P4 developers, but P4 is flexible to accommodate headers in the packet processing flow that are not part of the packet, okay? So there are these encrypted versions, I'll show this in a minute, there are encrypted versions of, like, the IPv4 header is completely encrypted. The FENC-IPR header has a chunk of it that's encrypted. Those are the headers that flow over the that flow over the wire. But when we're, for example, routing, we need the decrypted version of the IPv4 header, so we can, of course, look at the destination IP address and see what what route we used and what the next hop is. Okay, so sorry, I just noticed we have a question. LIC seems to replace MACsec. No, it doesn't replace MACsec. It has some. So first of all, MACsec is about signing. It does not actually encrypt the layer 2 header, and so that's a whole other discussion. But the LIC is not. There may be some commonalities. Let me put it this way: there may be some commonalities, but it's not meant to compete with MACsec. And plus, well, I'll just leave it at that because that's kind of off topic. But I'm happy to engage in more detail offline. Of course, we have the encrypted versions of this stuff that's flowing over the wire. But what we need to process on are the decrypted versions. So there are a couple of ways that we could have done this in P4, but it turns out that just defining another header and you just don't push that onto the packet before you send it out is what ended up to be kind of the easiest way. So that was kind of nice that you could just define another header, a plain text version of the header with the correct fields, use them like any other header, but you don't have to push them out. On the other hand, the gaps for this application are understandably because, as far as I know, encrypting headers like this has not really been done. So there are no primitive actions for encryption or decryption or digital signatures. And we can add them, and I did in this particular example, but that's platform dependent. So, and could be problematic or kind of a pain depending, which I'll get to in a minute actually. So here's some, finally, here's some P4 code samples. So here's first for headers, defining headers, of course. Here's an example of the header type that I call ENC for encrypted FENC-IPR type. And the fields are, we saw, they're the two short signatures, right? The shortened digital signature for the FENC-IPR, encrypted FENC-IPR header, the next shortened signature for the next header, which in this case IPv4, and the initialization vector for this header, and the encrypted bytes, right? That's it. The encrypted layer 3 header that arrives, arrives with the packet is just all encrypted bytes, right? In this case, it's 32 bytes. That's just all encrypted bytes. So that header is actually pretty easy. So down here is what the incoming frame looks like. The incoming frame has an L2 header. It has an encrypted FENC-IPR header, right? That certain chunk is encrypted, completely encrypted IPv4 header, and in this case, we also did an encrypted IPv4 payload. And the green here means, well, I guess I shouldn't have done the L2 header green, but the other green here is that these are encrypted. So this is what the encrypted, or sorry, this is what the incoming frame looks like, or the frame on the wire. What I call the internal working headers are the ones I mentioned that are not actually sent with the packets. They're the plain text version of those headers that are sent over the wire. So, get back out. For FENC-IPR, right here, you've got those first 3 fields are the same, and then you've got the 4 plain text fields. And this AES counter or shortened IB you can use for encrypting the next, we do use for encrypting the IPv4 header. So when that comes in the processing, which I'll show in a minute, is to check to calculate the short signature for what's coming in here for FENC-IPR, compare it to the one that's sent, and if it's the same, then we'll go ahead and decrypt. And if we decrypt it, we go from this encrypted FENC-IPR header to the decrypted, the plain text FENC-IPR header here. And now here's our FPID for account ID that we can use to route on. There we go. Oops. The next internal working header is just a standard IPv4 header plus, right? So I just didn't put all those standard fields in because you know, there are plenty of examples out there for them, but plus the options. So the required option to pad it out to 32 bytes. So here, for an option for IPv4, of course, we need to type it, and then the data that's in that option, and here it's 8 bytes, and then the end of options, the end of option identifiers here at the end, right? So then what we get is that if back here we take this next short signature and we compare it to, and then we calculate one for these encrypted bytes for the incoming layer 3 header, and if that checks out, then we decrypt the IPv4 header, and this is what we get, right? And then we can use this AES counter data to decrypt the payload in this particular example. Diagrammatically, here's what the ingress control looks like, and we'll see some of the code in a minute. So we can check the integrity. Well, first we need to check the integrity with that digital signature. So here's the FENC-IPR encrypted header dot this short sig. So here's that value of the short signature plus the symmetric logical interface key goes into calculating a short signature for that for the FENC-IPR encrypted FENC-IPR header. If that compares, you know, if that equals the one that was sent in this short sig, then we move on to decrypt the encrypted header, and we do that with with this same information over here. Sorry, the logical interface key plus the initialization vector, and we decrypt the encrypted header. And what comes out is the decrypted header, and of course, you know, that lick is still just hanging around. Then we take the next short sig, and we want to calculate the short signature for the encrypted layer 3, right? And now in this case, it's the forwarding path key. So we do it in the same kind of integrity check on the layer 3, encrypted layer 3 header. If that checks out, then we decrypt that, and of course we get out a layer, an IPv4 header, and once we have that, then we can do normal routing. So the code on that, here's the control, and this is a little out of order. I mean, it's a lot of code, and you know, couldn't exactly fit on the slide, so it might be a little out of order. But here's what the control ingress stanza looks like. And it's basically all those things, you know, applying tables for all those steps. First, you know, ingress, check the FENC-IPR header. And of course, if that passes, then we decrypt. And if that passes, we check the layer 3, encrypted layer 3. And if that passes, then we decrypt. And then if that passes, then we route the packet. So here's what the ingress check FENC-IPR table looks like. It reads the ingress port. We need the ingress port because now that's linked to the LIC, the logical interface key. And you know, that's the external table kind of thing. So we're going to match on, we're going to read and match on that ingress port, and we're going to get the logical interface key, symmetric in this case, that corresponds to that ingress port. And then the action is, you know, if we get a match, of course, and we should, then we're going to go to the check FENC-IPR action. And if we don't match, then we're going to drop the packet. Similarly, you know, here's the table for decrypt the FENC-IPR. So we need that ingress interface, logical interface key. And then here's another kind of flag variable that I set up. It's not really that interesting to all this, just kind of for tracking, so we'll just skip that. And then if we match on those, then, so basically this tells me, am I decrypting the FENC-IPR header, or am I decrypting the IPv4 header? Because how I populate the decrypted versions of the headers, those working headers, internal working headers, right, that matters. So, and I have just the same routine to do encryption and decryption, and then I populate the correct header based on that. So if I get matches here, then I decrypt and populate the FENC-IPR header, right? If I don't, then I drop it. And then, similar for check layer 3, right? So it's all very similar. Oops, and there's one more. So, and for decrypt layer 3. So the actions now to actually do the processing on the packets is to modify the fields. So I get these values that I'm going to use, and then calculate the short signature by calling a routine in all of this with all of these variables. So I need the calculated short signature. I need the encrypted bytes that I want to calculate on and check. I need the byte width because the FENC-IPR version versus the IPv4 encrypted header version, those actually the number of bytes that are encrypted are different. And I'm using the same routine, so it tells me what the encrypted byte width is. And then, minimize that. And then the logical interface key and the key byte width. Right. So I call this routine. This is an action. This is a routine that's actually now done in the hardware. In this case, the hardware is BMV2, and I'll show that in a minute. And here's another example to decrypt and populate the FENC-IPR, which would happen if this passes, right? If the check passes, which is going to be told by calc short sig, then we decrypt and populate the FENC-IPR header. So we modify the field for the, there's again another kind of tracking variable here, and then we call this routine decrypt AES-128 CBC with AES-128 in CBC mode. And so we need the FENC-IPR header is what's going to be returned. That's a decrypted one. We need an encrypted one, the byte width, the logical interface key, and the ID. Right. So if we take this stuff as input and run it through here, then it should return, or it should then populate the FENC-IPR header that we defined a couple of slides ago, and so on. Right. So same for layer 3. And then, of course, I did not show the routing action, because that's pretty much just what you would see with any other routing action. Egress control, a little bit simpler, because we can encrypt and sign first the layer 3 header. We're going to build the, take the plain text and build the encrypted version. So we just need to encrypt and sign it, and then build the encrypted FENC-IPR header. We take the FENC-IPR header, encrypt and sign it. And there are some housekeeping things we need to do with updating initialization vectors and things like that, counters and so on. But that's all pretty straightforward. And then finally, we send a frame. So the P4 code for that looks like, and it's pretty simple. So it's apply those 3 actions. So there's kind of the egress layer 3 table builds the encrypted layer 3 packet and calculates short signature on it. The same thing for egress FENC-IPR, and then the send frame is the usual kind of send frame where it just updates the MAC addresses. And in this example, just for expediency, I just I kind of stubbed in the static MAC addresses for the next hop for each router in the path. So the table for the egress layer 3 is, is make sure that first we want to match on the crypto select to make sure we're actually doing, layer 3 and not something else. Build the encrypted IPv4 header, and if we get a match, and otherwise drop it, right? And so that select match and exact, there's one value for layer 3 and one value for FENC-IPR. The table, what that looks like, again, there's it reads that select, so this is for the FENC-IPR. So we read the crypto select, and if it matches a value for FENC-IPR that we have, then we build the encrypted version of the FENC-IPR header. And finally, send the frame is right, the usual kind of thing. Sorry, just checking the questions. Still no more questions. Okay. So to build the FENC-IPR header, or sorry, the encrypted IPv4 header, we're going to track that flag variable basically, and then run the encrypt AES-128 CBC routine. And so we have encrypted layer 3. This is a header. It's the encrypted header, and then that's basically the output populating that header. But that was all one field of encrypted bytes. If you remember back from the header slide, and then the input to that is the IPv4 current IPv4 header, the encrypted layer 3 byte width, right, which in this case 32, the forwarding path key for this forwarding path, and the counter, basically the IV type of value that we're going to feed into the encryption as well. Right? And what comes out is the encrypted layer 3, and we calculate short sig. In this case, we're going to put it in this calc short sig temporary variable. Basically, it's a metadata variable, and then we're going to take those encrypted bytes, the width, and the FPK, the forwarding path key, and its byte width. We're going to take all those and then run the calculation and sort in this variable. And then once we get it back, we're going to then put that value into the next short sig. And I did it this way because it seemed like for BMV2, which is in C++, that it wouldn't work just directly putting in a value like this, or at least it was beyond my C++ programming capability looking at the BMV2 code, which I'll get to in a minute, which I really kind of am in awe of what they wrote, but it's, I'm not that much of a C++ programmer. And then finally, we modify the value of the crypto select to say that we're getting ready for the next encryption action, which is to do the FENC-IPR. And the FENC-IPR is similar, very similar. It's the same encryption and signature routines, just with all the FENC-IPR data instead of the IPv4 data. Okay. Okay. So code sample, BMV2. So here's my my take on BMV2. It was really great to use, but like I said, I'm not much of a C++ programmer, and this is like really C++. I mean, with stuff that I just really didn't know. I'm primarily programming in Python and C. So it was actually kind of painful for me personally to go in and modify the code. I mean, finding modify was not a problem, but this is just my experience, which I come from more the network engineering side rather than the code development side of all this kind of stuff. So for me personally, it was kind of painful to modify the C++ code and put in primitives for for the encryption stuff, for encryption, for decryption, for digital signature calculation. But here's just, this is not even really code, it's just showing kind of the headers and stuff. In BMV2, there's this, I use the simple switch version or implementation with BMV2, and there's a file primitives.cpp that has primitive actions in it. They're all defined, and for example, added this added the code to calculate the short signature. And so here's the header, just the first line for that, and then you've got and there's a lot of code. Well, actually, it's just about all of it, because most of the code is not defined actually in the C++ source file. There's a lot of code that's actually defined in header files, which to me, being a C programmer primarily, was kind of strange. But I just went with the flow in this case, pun intended. So here it takes, here are all the field types that it takes, right? And those field types are defined up here by your call. So here's calc short sig. So here's the short sig. Here's encrypted layer 3 bytes, etc. And so there are only a certain number of basic data types in BMV2, and data is kind of the most flexible. So everything here is a quote data type. Sorry, just checking the time. We're still pretty good on time. Here's the so the destination, that's a destination variable we're going to put the information into. The source information, the source size, the key size. And then the way BMV2 is set up is that now we can, since dest is a data type, we can do the calculation calculate the short sig and put it in that variable by calling dest.calcShortSig with these arguments. Okay, and now this calcShortSig is code to actually do that is defined now in this, and it's very long, so I didn't include it in here. In this data.h header file, and here's where it's defined with there's a source size, key size, and it goes through and does a SHA-256 calculation on the data that's provided in source, and then inside that code, right, this has a void return type, but inside that code then it actually populates that dest variable. And then there are similar kinds of code implementations for the encrypt AES-128, and then there's the decrypt AES-128 CBC, and so on. Right, so that was actually the longest, hardest part. The P4 type was great. So, lesson learned. It's much less interesting, but if you want to do something easy, don't do something where you have to define new primitives. So I'm hoping that this will end up being interesting. It's still very much early work. Hoping it will be interesting enough that someone who's in this case for BMV2, someone who's a real C++ programmer can take that and turn it into something much better. So that's BMV2, and so on the Agilio, which we have, that's another thing that I'm working on now. And so in that case, to add those primitives is not C++, of course, it's C, which I started out working on this with Agilio and was having problems that were due to me. So I thought, okay, I'll take a step back and try BMV2 first, and then so I did that, and now I'm working on trying to put it back into run it through Agilio. So finally, this is basically the last slide. Shows the networks that I'm using, quote networks I'm using in this development, in this prototyping. Everything that's in a gray box is I do everything on Linux, and so everything in a gray box, well, of course, except some of the Agilio work, because that IDE is only on Windows, but I use Windows when I have to only. And so all of this work is done on Linux, and it's just easiest sort of to, in networking terms, to use network namespace isolation. So everything that's in a gray box is NetNS isolated from other things, right? It's in its own NetNS namespace. So there are just these two hosts with a BMV2 router in between, and just try to send packets encrypted out of one host, which is just a Python, simple Python program that creates the bytes and sends them out using SCAPI. So it creates the headers and then encrypts the headers so that the pictorial view we saw before of a fully encrypted, 32 bytes of encrypted IPv4 header and 16 bytes of out of the, actually it's 48 bytes, not 32. I misspoke before. 48 bytes total of the FENC-IPR header. And just sample data that's also encrypted. It just generates those bytes and then sends them out using SCAPI, which I love. So then it comes into the BMV2 instance, this R1, and is, oops, there's the mouse. Comes into this BMV2 instance and is acted upon by all this code, and then is sent to here, and I watch at each end, printing out what's sent, the plain text version of what's sent, and on host A, and the plain text version of what comes in on host B after it's decrypted, and are those the same or not? And they are. Right, so it works correctly going through that BMV2 instance. The next step was this two host for router kind of thing. So R134 is the actual path. Those have the and 2 is also a BMV2 instance. So just to show that, yeah, we can do this through more than one router, and all the MAC addresses and separate, right? So this, from this interface to on R1 to that interface on R3, that has its own lick that's different from the logical interface key from R3 to R4 here, right? So just to, those keys were all stubbed in. MAC addresses were all kind of stubbed in the P4 code and tables for expediency, and we're able to do the same kind of thing, show the bytes that are being sent out before they're encrypted in host A, sniffing and showing that they are encrypted on the, in between the routers, in between the hosts, and between the routers, and then when it comes out on the other end, we can decrypt it. And then finally, the last one here is shaded, because this is still kind of working on, is to replace one of the routers, one of the BMV2 instances, sorry, with actual hardware. And so all this stuff that's NetNS isolated is running in a VM basically, and we, instead of running up through 1, 3, 4, we're going to run through 1, 2, 3 and send stuff out of that VM and the machine it's on into the machine with the Agilio card, and then forward it back up into that original VM on that original machine and over to here, right? So the same idea, just try to do it now with some actual hardware. So that's what we've done. Thanks for listening. I appreciate your attention. And if there are any questions, I'm happy to answer. Also, if anyone wants to contact me, it's mark.matties@jhuapl.edu.
Mark, thank you very much. We really appreciate it.
So I hope that was useful.
It was useful.
And interesting.
It was definitely
at least useful, if not interesting.
Sounds good. Yep, and everybody, we will have these slides and the replay of this webinar up on our Open-NFP classroom page shortly. Thanks, everybody.